he's going to tell us about the constraint of dark matter sterile neutrino with the Germanium detector. Okay, also closed condensed matter. Okay, welcome, Lucifer.
So my collaborator include Chen Junwei and Liu Chenbang, Ji Xingchang from Donghua University, and Wu Ziliang, and some people from the Xinka, include Wang Zijing. So the domain search, I think, is a well-motivated target because we know that there are a big missing part in our universe. So I suppose I don't need to emphasize how important the dark matter is, and I can go further for some more detail about how we search for the dark matter. So in this comic, you can see this yellow arrow is the time evolution direction. So from this direction, you can see from this direction you can see two dark matter comes in and becomes the particle. So this is so-called indirect detection. In this, so people search for the signature from the dark matter, like E plus, E minus, or photons. So for example, for MS2, try to looking for the universe for some high energy electron and positron, and found their ratio have some abnormal behavior in certain image. So this may come from the dark matter annihilation. So for the revised way, you can see people can also accelerate the same model particle to a very high energy, and correction can have some new unknown particles. And the last one in this direction, so-called direct detection. That means that people can use some standard model particle, try to see try to observe the interaction signal between the dark matter and standard model particle. And in this talk, I'm majorly focused on this direct detection. So this kind of shows that how people do experiment in the world or searching for waves. So you can see that the interaction between the dark matter and the normal particle that will give real detectors a recoil energy, and this recoil energy can transfer to for the annihilation or excitation will become a vibration. So this signal will become like a electron current, and we can detect like electron moving in your detector, or become a light, or even become a heat. So in my topic, I would say we're using germanium detector, which is like a semiconductor, and they are majorly focused on try to measure the ionization. And for the advantage for using the germanium detector is that the germanium we can absorb the recoil energy with a higher resolution, and also we can detect lower recoil energy. So that's the advantage for germanium detector. So that's how people do a direct detection. And now because we don't know the actual interaction between dark matter and standard model particles, but we can still write down some effective Lagrangian. For example, we can write down some like contact detection, effective contact detection, or effective trap-like detection. We can build a model with spin independent, or even we can have a spin dependent vector. Once those Lagrangian, effective Lagrangian has write down, then we can drive a cross-section for this kind, for every kind of interaction. So that's how we do the constraint on dark matter. So now I'm going to talk about sterile neutrino. This is a one candidate of the dark matter, and it's proposed to explain the origin of the neutrino mass. So this sterile means that you don't have the electromagnetic force, weak interaction or strong interaction. They only have a gravitational interaction. And this is a hyper-theoretical particle, and the mass region depends on your model. So now people are interested about KEV sterile neutron. It's because that we have some experimental group shows that they have a abnormal X-ray emission line at around 3.55 kV on the universe. So there may be a scenario of the sterile neutron decay to maybe a normal and couple into a photon. And this is and for theoretical part, there are some model which so-called minimal extension standard model, which just based on the original standard model and put some correction, a little correction. For example, add the 3 right-handed neutrino into the original standard model, then they can expand the neutrino masses. And this masses, so for those model, for example, this new NS model, they have the lightest sterile neutrino around this KE region. This region is determined by the current neutrino mass bond, by the seesaw effect. So we can set a bond on this sterile neutrino. So this KV neutrino become a hard issue because of those astrophysics of observation. So we can assume if we have this kind of coupling between the sterile neutrino and the photon, then we can see this photon X-ray, and if we can measure lifetime, then we know how strong the coupling it is. But what if we have this kind of coupling, this photon can also couple to the electromagnetic force with normal matter. So this is typical indirect detection. So we can also do a similar direct detection by couple this photon to a normal matter with electromagnetic force. So this sterile neutron comes in, become sterile model neutrino, and there's a virtual photon coupled to your detector, for example, like germanium atom. And this kind of detection is quite similar with the neutrino scattering with the detectors. But major difference between the sterile neutrino constant or normal neutrino constant is that for normal neutrino constant, the stream momentum transfer is always larger than the energy transfer. So the form momentum transfer is always negative. But for this kind of very massive but slow sterile neutrino comes in and become a very light and very fast neutrino. Because there are a lot of mass energy in the final state, so at a certain t and scaling angle, then this form momentum transfer will become positive. So it means that for ordinary neutrino scattering, then there is always space light. But for this special sterile neutrino oscillate to a normal neutrino, this non-standard interaction, we have a space-like corresponding to a time-like structure. So the causation will have a very different form. So we can distinguish these two kinds of events. So then we can write down differential cross-section, and then this Q square is come from a virtual photon propagator, and we can separate to a longitudinal part and transverse part based on the direction of photon momentum. So the response function means that we have a atomic transition for your detector. So from initial state to a final state, we have a response, detector response function, and we also have some kinematic factor due to the interaction Lagrangian of your sterile neutrino, depends on your coupling. So once you write down the form momentum, this can be expressed by the incident energy and transfer from the stereo neutrino, and cosine theta is the scattering angle. So for this kind of detection, we know that Q squared can be 0 as some T and theta. So you can see that there's a Q to the fourth, but in this turn, we only have Q to a 2 or even 0, so they may have some problem. So the physical institution for this Q squared equal to 0 means that there is unsure limit, which is that the photon is become real when the T equal to for H equal to the momentum. So this scaling process is no longer distinguishable from a two-step process, like stereo neutron first decay to a neutrino and photon, and this photon come to your detector and have some signal. So once you know that two-step process, we have a real photon propagating in your detector. That means we know that electromagnetic wave propagate in media. Their momentum will have a damping factor. This factor is due to the media. So we can see that we have changed the momentum of the photon to this effect with this additional terms, which this is depicted by the number density of your detector and how strong your detector media interaction with the photon. So once we made a correction on this real photon, then we have a regularized differential cross section here, and this can be used to do some calculations. And we also can have some approximate screen. For example, like EPA, we're using we approximate the stereo neutral constant like a real photon. Then we can approximate the response function by photo absorption data, or like another approximation like FEA, which treat the target like free electron. So we can quickly go to some result. This result is based on hydrogen, because hydrogen can have a negative wave function, so we can quickly do a negative result. So we can see we fix the velocity and increase with mass. We can see this is a peak, and this peak is due to the real photon limit. So, and this T is around the half of the mass. So around this region, we will force the real photon limit. Then we have a very strong enhancement, and we can see with the increase of mass, this peak, another peak is here. This is due to the phase space condition of your atomic transition. And we can see we can also fix with the masses and increase with the velocity, or increase the momentum of the stereo neutrino. We see this region become broader, but the value become lower. Also,
1 minute.
Okay. Also, we can have some result with germanium. The result is similar because germanium have many orbitals, so the structure for this space condition is become more complicated. So the most important contribution comes from this enhancement, and this enhancement is well approximated by EPA. So we can do a quick analysis on EPA because it is due to the real photon limits. So we can quickly get a simple, very simple form for the value of this enhancement region and also the boundary. So can you see that this enhancement region is proportional to the inverse of the momentum square, and their region is about proportional to the momentum. So once we can given mass and velocity, then we can have this kind of enhancement region, and this enhancement region can fit in with the experimental data. Like this is data from external collaboration. So then we can quickly make a constraint on the coupling strength by a direct detection. And this can also compare to indirect detection. But indirect detection only have one kind of mask. We can extend to different masks. So that's about my presentation. Thanks.
Very challenging project. One question. No? So basically, you are not involved in any experiment. Just theory you are doing.
Yeah, but we have collaborated with external from external income, which is one thing. They are basically using Germanium detector to constrain neutrino property, but their detector can also use for diameter search.
I think due to constraint time, thank you. Okay.